Hello there, and welcome. Tonight, I want to take you somewhere that might feel unfamiliar at first, yet somehow deeply familiar all at once. I want to invite you into a space, literally and figuratively, where we can explore one of the most beautiful mysteries that humanity has ever encountered. A mystery that sits above us every clear night, waiting patiently in the darkness, glimmering softly with light that has travelled an almost incomprehensible distance to reach your eyes. Before we begin this journey together, I want to ask you to join our community. If you love cosmic journeys like this, if you feel that pull toward the stars and the questions they inspire, please consider liking this video and subscribing so you don't miss any of the contemplative explorations we share together. And I'm genuinely curious. Where are you watching from right now? What time is it where you are? Is it late evening, the middle of the night, or early morning? Let us know in the comments below. There's something special about sharing this moment across different time zones, different parts of the world, all of us looking up at the same sky, all of us wondering about the same mysteries. You see, there's a question that lives in the minds of astronomers, philosophers, and anyone who has ever paused to really look at the night sky. It's a question that might seem strange when you first hear it, that might even feel a bit unsettling in a way you can't quite put your finger on. But I want to tell you something right from the start. This question isn't meant to alarm you. Instead, it's meant to fill you with a kind of gentle wonder, the kind that settles into your mind like a leaf, drifting slowly through still water. The question is this: what if the most distant light that the human eye can see, the light that has guided sailors and dreamers for countless generations, what if that light was becoming something we would eventually lose? What if one of our most precious cosmic neighbours was slowly, gently, inevitably fading from our view? What if, just perhaps, we are living in a brief shining moment in cosmic history when we can witness something that future humans may never see? This thought might sound like something belonging to ancient myths or distant prophecies, but it's actually rooted in something far more tangible. It's rooted in the physics of light itself, in the nature of an expanding universe, and in the particular dance that our nearest major galactic companion has been dancing with us for billions of years. We're talking about Andromeda. Not the mythological princess, though there is a certain poetry in that name. We're talking about the Andromeda galaxy, that luminous spiral of billions of stars that you might have seen yourself if you've ever found a truly dark place on Earth and looked toward the northeastern sky on a clear autumn evening. It appears to us as a gentle smudge of light, an elongated oval that seems to glow with an ancient, timeless quality. But what we're looking at isn't just a smudge. What we're seeing is a galaxy, a vast collection of hundreds of billions of stars, each one potentially surrounded by its own planets, its own worlds that might harbour their own mysteries and wonders. And here's where the mystery deepens, where it becomes something that perhaps you've never considered before. That gentle light you might have seen with your own eyes has been travelling for an enormous amount of time to reach you. Think about that for a moment. Really let it settle in your mind. Every single photon, every tiny particle of light that has entered your eye when you've gazed at Andromeda has been on a journey. A journey that began not days ago, not years ago, not even centuries ago. It began 2.5 million years ago. 2.5 million years. To put that in perspective, modern humans, you and I, the kind of humans who think and feel and wonder about the cosmos, we've only existed for a few 100,000 years at most. The light you see from Andromeda right now left that galaxy long before your species ever existed. It travelled through the vast, empty darkness of space, passing by countless other stars and galaxies, navigating through the expanding fabric of the universe itself, all to reach you on this particular night, at this particular moment in time. There's something almost sacred about that, isn't there? The idea that we are recipients of a message, a beacon of light from the ancient past, delivered across an almost unimaginable distance. And yet this beautiful phenomenon, this gift of ancient light that we've received throughout all of human history, carries within it a secret. A secret that only became clear to us in relatively recent times, as our understanding of the universe deepened and our tools for observing the cosmos became more sophisticated. A secret that might sound like sadness at first, but which, as we explore it together, reveals itself to be something far more profound. And if you're finding these ideas interesting, if you're feeling that sense of cosmic curiosity beginning to unfold in your mind, I'd love for you to comment in the section below and tell me what's capturing your attention so far. What aspect of this cosmic mystery speaks to you? What draws your wonder? Because this journey we're on together, it's enriched by knowing that we're exploring it together, that your curiosity is intertwining with mine and with everyone else who is listening tonight. The thing about cosmic mysteries is that they don't announce themselves with fanfare or drama. They reveal themselves slowly, gently, through the patient observation of scientists who spend their lifetimes studying the heavens. They reveal themselves through the accumulation of data, through the careful measurement of light, through the patient piecing together of clues scattered across billions of light-years of space. And the mystery we're exploring tonight, the mystery of why Andromeda's light will never reach future humans, it's one of those mysteries that only becomes apparent when you understand several seemingly unrelated pieces of cosmic truth. It's a puzzle that requires us to understand not just what Andromeda is, but how light travels, how the universe expands, and what that expansion means for the future of observation and wonder. I know that some of you might be skeptical right now. You might be thinking, but that's impossible. We can see Andromeda tonight, so how can we say it will become invisible? And that skepticism is healthy. That's the kind of curious doubt that leads to deeper understanding. It's not quite accurate to say that Andromeda will simply vanish, like a light switch being turned off. What we're really talking about is something far more subtle and, in its own way, far more interesting. We're talking about what happens when light itself changes its nature as it travels through a universe that is fundamentally continuously expanding. We're talking about the way distance transforms light, stretches it, shifts it into wavelengths that human eyes were never designed to perceive. We're talking about a process that is already happening right now, at this very moment, but which will continue inexorably into the future, carrying Andromeda further and further beyond the reach of human observation. To understand this, we need to start with something quite basic but also quite profound. We need to think about what light is and what it means when light reaches us from distant places. When you look at a star or at the Andromeda galaxy, you're not actually seeing the star or the galaxy as it is right now. You're seeing it as it was. You're seeing a ghost of the past made visible. This is true of all light from distant sources. The farther away something is, the longer its light takes to reach you, and therefore the further into the past you're looking. If you were somehow able to look at the sun with a delay of 8 minutes, which is the time it takes sunlight to reach Earth, you would be seeing the sun as it was 8 minutes ago. If you could look at the nearest star to our sun, Proxima Centauri, which is about 4.4 light-years away, you would be seeing it as it was over 4 years ago. And when you look at Andromeda, 2.5 million light-years away, you're looking at a ghost, a memory, an image of the way that galaxy appeared 2.5 million years in the past. This concept, that we see distant objects as they were in the past, it's one of the most beautiful and disorienting ideas in all of science. It means that when you look up at the night sky, you're not looking at the current state of the universe. You're looking at a history, a vast timeline of moments stretching backwards through time. You're looking at a cosmic museum, where each star and each galaxy is a photograph from a different era. And Andromeda, that gentle glowing spiral, it's a photograph from an era when your species barely existed, when the Earth itself was undergoing its own transformations, when the whole world was different from what you know today. Yet that light has patiently made its way across all that distance and all that time to reach you tonight. Imagine it. Imagine the journey of those photons. Imagine light particles embarking on a voyage that would take longer than the entire history of human civilization as you know it, traveling through the void at the fastest speed that anything can possibly travel, never stopping, never resting, just pressing forward through the darkness toward a destination they could not know, toward human eyes that wouldn't exist yet, toward a world transformed beyond recognition. This is the poetic reality of looking at distant cosmic objects. This is why looking at the night sky is such a powerful meditation, such a profound moment of connection between our small human minds and the vast machinery of the cosmos. Every star you see is a time portal. Every galaxy is a message from the past. And when we understand this, when we really let this sink in, we start to ask different questions. We start to wonder not just about what we're looking at, but about what it means that we're seeing it at all. We start to contemplate the nature of light and time and the fabric of reality itself. And perhaps most importantly for our journey together tonight, we start to understand what might change about this relationship between observer and observed as time marches forward into the future. The Andromeda galaxy is particularly special because it's the most distant object that the human eye can observe without any kind of technological aid. There are billions of galaxies in the observable universe, each one containing billions of stars, yet the vast majority of them are too far away, too faint to see with the naked eye. You need telescopes to find them, to coax their light from the darkness, to capture their whispers of information from across cosmic distances. But Andromeda is different. Andromeda is close enough, bright enough, that on a clear night in a dark location far from the light pollution of cities, you can see it with your own eyes. You can go outside and look up and actually receive photons that have made a journey of 2.5 million years and let them strike your retina, be processed by your brain, and become part of your direct experience of the universe. This makes Andromeda something almost sacred in a way, something that connects you directly to the cosmos without any intermediary technology. It's a bridge between the human and the infinite. And perhaps that's why the thought that this light might one day become invisible to future humans carries such weight. Perhaps that's why, as we explore this mystery, we feel a kind of gentle melancholy mixed with our wonder. Because what we're really contemplating is a kind of loss, but not a loss in the way we usually think about loss. We're not contemplating the destruction of Andromeda. The galaxy itself will still be there. It will still exist, still spin gracefully through space, still contain hundreds of billions of stars. What we're contemplating is something far more subtle and perhaps far more profound. We're contemplating what happens when our ability to observe something changes. We're contemplating the way that the expanding universe, in its patient, inevitable way, can transform a visible light into an invisible whisper of radiation that no human instrument, no matter how advanced, could possibly detect. It's in contemplating these ideas that we begin to grasp the real mystery at the heart of tonight's journey. And I think that if you're still here with me, if you're still engaging with these ideas, then you're beginning to understand why this matters. You're beginning to see why scientists, philosophers, and stargazers have found this question so compelling. So please, if you're still finding value in this exploration, if there's something in these cosmic ideas that's sparking your curiosity or your sense of wonder, let me know in the comments. Tell me what you're finding most interesting so far. Are you drawn to the physics of light? Are you captivated by the distances involved? Are you moved by the philosophical implications of seeing ancient light from the past? Your engagement helps us build a community of cosmic explorers, and it helps me understand what aspects of these mysteries resonate most deeply with you. Now, as we prepare to move deeper into this exploration, I want you to find yourself getting more comfortable, more settled. If you're in bed, let yourself sink a little deeper into your pillow. If you're in a chair, let your body relax, let the weight of your day begin to dissipate. Because the journey we're on is not a race. There are no deadlines, no finish lines, no moments where we need to hurry. We have all the time in the world, or perhaps more accurately, we have all the time in the universe, which is something rather different and far more expansive. And as we move forward, as we begin to explore the actual science behind why Andromeda's light will fade, I want you to remember this moment, this peaceful place we've created together, because we'll return to it again and again as our journey continues. We'll return to this sense of wonder, this sense of connection across vast distances and deep time, and we'll build upon it layer by layer until we have a complete understanding of one of the most beautiful mysteries that the cosmos has to offer. The thing about understanding cosmic mysteries is that understanding them doesn't diminish their wonder. It doesn't make them less beautiful, less profound, less worthy of our awe. In fact, often the opposite is true. When we understand the mechanisms behind something, when we see how nature works in its patient, elegant way, the wonder only deepens. The beauty becomes more intricate, more sophisticated, more worthy of our contemplation. And this is what we're going to discover together over the course of this journey. We're going to learn the mechanisms. We're going to understand the physics. We're going to see how light behaves, how the universe expands, how distance and time and the nature of reality itself conspire to create this particular mystery about Andromeda. And as we do, I think you'll find that the wonder doesn't fade. Instead, it transforms. It becomes something more nuanced, more philosophically rich, more deeply connected to questions about existence itself. So settle in, get comfortable, Let your mind begin to drift into the vast spaces we're about to explore together, because we're about to learn about the ancient light that Andromeda has been sending toward us, light that has traveled through the darkness for longer than human civilization has existed, light that has been carrying a message from our galactic neighbor, a message written in the language of particles and waves and the fundamental forces of nature. And as we learn about this light, as we trace its journey from its origin in the distant past to its arrival at our eyes in the present moment, we'll begin to understand what fate awaits it in the future. We'll begin to see why, despite the light reaching us right now, despite Andromeda being visible in our skies, there comes a time when that visibility will change. There comes a time when the light, still traveling, still existing, will transform into something that the human eye can no longer perceive. There comes a time when Andromeda will truly slip into the cosmic darkness, not because it has been destroyed, but because the universe itself, in its expansion, will have made that vision impossible. And that time, that transformation, that's the real heart of what we're exploring tonight. That's the mystery that we're going to unravel together, piece by piece, moment by moment, as we journey deeper into an understanding of cosmic physics, time, distance, and the nature of light itself. So let's begin this journey in earnest now. Let's start with the most basic and yet most profound question. What is this ancient light that we're seeing when we look at Andromeda? And what does it mean that this light has been traveling for so long to reach us? There's something that astronomers have known for a long time, something that might seem obvious when you first hear it, but which becomes more and more profound the longer you contemplate it. It's this: light is not instantaneous. Light does not simply appear everywhere at once. Light travels. It moves from place to place at a specific speed, the fastest speed that anything in the universe can move, but a speed nonetheless. That speed, by the way, is approximately 186,000 miles per second, or about 299,000 kilometers per second. It's a speed so fast that it seems instantaneous in our everyday lives. Light from the other side of the room reaches your eyes almost immediately, so fast that you perceive things as they are happening right now. Light from the sun takes about 8 minutes to reach Earth. Light from the nearest star takes over 4 years, and light from Andromeda takes 2.5 million years. When you internalize this, when you really think about what this means, it becomes clear that sight, the ability to see, is fundamentally a form of time travel. When you see something, you're not seeing it as it is at this moment. You're seeing it as it was at some point in the past. The closer something is, the more recent that past. The farther something is, the more distant that past. And for Andromeda, that past is incredibly distant indeed. The light that enters your eye when you gaze at Andromeda at night has been on the road for 2.5 million years. It began its journey when your species didn't yet exist. It began its journey in an era so distant that the ice ages had come and gone, when saber-toothed cats hunted across the plains of Africa, when the world was fundamentally different from the world you know. Think about the journey of a single photon, a single particle of light, originating from a star in Andromeda. Perhaps it originates from the core of that galaxy, from the region where millions of stars cluster together in the dense heart of that spiral. Or perhaps it originates from one of the outer arms, one of those beautiful curling structures that give spiral galaxies their characteristic shape. Regardless of where it originates, the moment it begins its journey, it's committed. It will travel in a straight line, assuming nothing deflects it, through the vast emptiness of space. It will travel at 186,000 miles per second, which means that every second it covers a distance equal to 7 times the circumference of Earth. Every hour it covers a distance equal to the distance from the Earth to the Sun, about 270 times over. And yet, despite this incomprehensible speed, it will still take 2.5 million years to cross the gap between Andromeda and the Milky Way. What this tells us is something staggering about the distances involved. It tells us that the gap between us and Andromeda is so vast that even travelling at the fastest speed anything can travel, it takes longer than the entire existence of modern humanity to cross it. It tells us that space is not just big, it's incomprehensibly, almost unfathomably vast. The distances between galaxies dwarf any distance that exists in the solar system. The solar system, which contains the Sun and all of its orbiting planets, is almost nothing on cosmic scales. The Sun's influence, the zone within which its gravity can hold planets, extends maybe a light year or so outward. But that's just the Sun. The distance to the next nearest star is over 4 light-years. The distance to Andromeda is 2.5 million light-years. The universe, it turns out, is incomparably larger than our everyday experience of distance has prepared us to understand. And yet, despite this almost crushing vastness, the light still comes. Across all that empty space, across all that distance, the photons still travel. They still persist. They still carry information about their source, and in doing so, they create a connection. They create a bridge across the void. They create a way for you, sitting here on Earth, to have a direct physical connection to a galaxy so distant that it lies on the other side of the universe's visible horizon, at least from many perspectives. When you see Andromeda, you're not just seeing a light show. You're not just seeing something pretty in the sky. You're receiving a message that has traveled across incomprehensible distances and incomprehensible time. You're receiving information that was generated in the depths of the past and delivered to you, intact, across the void. This is why astronomers and cosmologists speak of light from distant objects with such reverence, such wonder, because light is information. Light is the way the universe communicates across vast distances. Light is the medium through which the cosmos reveals itself to conscious observers like us. Every photon that reaches your eye is a tiny messenger, carrying news from a distant place and a distant time. And the light from Andromeda, this light that appears to us as a gentle glow in the night sky, carries within it messages that are 2.5 million years old. It carries within it information about what was happening in Andromeda when dinosaurs still walked the Earth. Wait, no. Dinosaurs were already extinct by then. Let me correct that. It carries information about what was happening in Andromeda in an era so ancient that modern humans barely existed yet. It carries information about the composition of stars, about the density of gas, about the dynamics of that vast spiral galaxy at a time when the world below was so different. And perhaps most profoundly, this light carries within it something almost philosophical. It carries a kind of testimony to existence. It says, I existed, I am here, I have crossed this distance, I have persisted through time and space, I am real, and my reality extends across the universe. Each photon from Andromeda is a small voice calling out across the darkness, and humans, for all of our existence, have been listening. We have been receiving these messages. We have been able to see, with our own eyes, a galaxy that is incomprehensibly distant and incomprehensibly ancient. Now you might be wondering, as you lie there and contemplate the journey of this light, what it means that we're receiving this light right now. You might be wondering if this situation is permanent, if this bridge of light will always exist between us and Andromeda, if future humans will always be able to look up and see that gentle glow in the sky. And that's where our mystery deepens. Because the answer, as we're going to explore, is more complex and more interesting than a simple yes or no. The answer involves understanding how the universe works on the grandest scales, how space itself behaves, and how that behavior will change the nature of the light that reaches us from Andromeda in the future. But before we dive into that aspect of the mystery, I think it's important to really sit with what we've discovered so far. It's important to really contemplate the profound reality that when you look at Andromeda, you are looking at something incredibly ancient. You're receiving light that has traveled a distance beyond human comprehension. You're having a direct physical encounter with something that exists at the far reaches of the observable universe. This is not a small thing. This is not a casual observation. This is a profound cosmic moment, and you're having it right now. The light that enters your eye has been on its way for 2.5 million years, and it's just now reaching you. At this particular moment in cosmic time, that's a remarkable thing. That's something worth pausing to truly appreciate. And so, as you continue to listen to this exploration, as we continue to move deeper into the physics and the philosophy of what this light means, I want you to carry with you this sense of connection. I want you to remember that when you see Andromeda, you're seeing something real, something distant, something ancient, something that has persisted across incomprehensible distances. You're seeing a mirror of your own place in the cosmos. You're seeing a reminder of how vast the universe is and how small you are within it, but also how remarkable it is that you can perceive this vastness at all, that you can receive these messages from across the void, that you can contemplate your place within the grand machinery of existence itself. This ancient light, this light that has traveled 2.5 million years to reach you, is the foundation of everything we're about to explore. It's the baseline of our mystery. And as we move forward, as we begin to understand how the universe expands, how space itself stretches, and how that expansion will eventually transform this light into something else entirely, remember that we're building on this foundation. Remember that beneath all the physics and all the data and all the cosmological observations, there is this simple, profound reality. Light travels. It carries information across vast distances and vast times, and for as long as humans have existed, Andromeda's light has been reaching us, carrying messages from a galaxy so distant that we can barely comprehend the distance. The universe is sending us these messages, has been sending them for eons, and we have been fortunate enough to receive them. But is that good fortune destined to last forever? Will future humans gaze up at the same sky and see the same gentle glow? Or is there something about the fundamental nature of the cosmos that will eventually change this situation? That will eventually close this channel of communication between us and our distant galactic neighbor? These are the questions that will guide us as we move deeper into our exploration. These are the mysteries that we're going to unravel together, piece by piece, as we learn about the expanding universe and the fate of light in a cosmos that is growing, stretching, and continuously transforming itself in the vast silence of space. And so, now that we have established this foundation, now that we understand the basic reality of light traveling across vast distances, let me invite you to move with me into the next layer of our exploration. Let me invite you to contemplate something even larger, even more vast, even more wonderful than the simple fact of light traveling. Let me invite you to think about the universe itself, not as a static thing, not as a thing that remains eternally the same, but as something alive, something dynamic, something that is fundamentally changing at every moment, at every scale, throughout all of space and all of time. Because it's only when we understand this aspect of the cosmos, only when we grasp what's happening to space itself, that we can truly begin to understand the mystery of why Andromeda's light will never reach future humans. It's only then that the full profundity of our cosmic situation becomes clear, and we begin to see ourselves not just as observers of an ancient static universe, but as inhabitants of a cosmos in the midst of a grand ongoing transformation. The idea that the universe might be expanding, that space itself might be stretching and growing, is actually not that old as scientific ideas go. For most of human history, people believed that the universe was static. They believed that the stars were fixed in place, that the distances between them never changed, that the cosmos was eternal and unchanging in its fundamental structure. This made sense in a way, because on human timescales, across the span of a single lifetime, or even across the span of human civilization, the stars do appear fixed. The constellations remain the same. The arrangement of the heavens seems constant. But in the early 20th century, something remarkable happened. Astronomers, using increasingly sophisticated telescopes and measurement techniques, began to discover something extraordinary. They began to discover that the universe was not static. It was moving, galaxies were moving, and not just in random directions, but in a systematic way. An astronomer named Edwin Hubble made observations in the 1920s that forever changed our understanding of the cosmos. Using one of the most powerful telescopes available at the time, the 100-inch Hooker telescope in California, Hubble was able to measure the light from distant galaxies with unprecedented precision. And in analyzing that light, he made a discovery that would reshape cosmology. He discovered that the light from distant galaxies was systematically shifted toward the red end of the spectrum. This phenomenon is called redshift, and it tells us something profound about motion. When a source of light is moving away from you, the wavelength of that light gets stretched. The light becomes redder, shifted toward longer wavelengths. This is a phenomenon called the Doppler effect, and we're familiar with it in everyday life. When an ambulance or police siren moves away from you, the sound it makes gets lower in pitch. That's because the sound waves are getting stretched as the source moves away. The same thing happens with light. If a galaxy is moving away from us, its light gets stretched, becomes redder. Now, Hubble didn't just observe one galaxy with this redshift, he observed many, and he made a stunning discovery. The farther away a galaxy was, the more redshifted its light was. In other words, the farther away a galaxy is from us, the faster it appears to be moving away from us. This relationship, which has come to be known as Hubble's law, revolutionized our understanding of the cosmos. It suggested that the universe was not static. it was expanding. And not expanding in some small localized way, but expanding everywhere, in all directions, on the grandest scales possible. Imagine a vast balloon being inflated. As the balloon expands, the surface stretches, and objects on that surface move apart from each other. The farther apart they start, the faster they move apart as the balloon expands. That's roughly what's happening with the universe. Space itself is expanding. Galaxies are being carried apart by that expansion, and the farther apart they are, the faster they're being separated from each other. This was a genuinely stunning revelation. It meant that the universe had a history. It meant that the universe was not eternal in its current state. It meant that there had been a time in the past when everything was closer together, when the universe was smaller, denser, hotter, and it suggested that there might be a time in the future when everything would be farther apart, when the universe would be larger, less dense, colder. The discovery of cosmic expansion was one of the great intellectual achievements of human civilization. It changed the way we understand reality on the most fundamental level, and more specifically for our purposes tonight, it changed the way we need to think about light from distant galaxies. Because if space is expanding, if the distance between us and Andromeda is increasing over time, then that has profound implications for the light that's traveling between us. Think about it. Light is traveling toward us from Andromeda at the speed of light, approximately 186,000 miles per second. That's incredibly fast. And yet, at the same time, space itself is expanding, which means that the distance between us and Andromeda is also increasing. The photons are traveling toward us, but the space that they're traveling through is stretching, pulling the source of those photons farther away. It's almost like trying to reach someone by swimming toward them while they're being pulled away on a boat. You might be swimming as fast as you possibly can, but if the boat is being pulled away faster than you can swim, you'll never reach them. The situation with light from distant galaxies is even more complex because the expansion rate of space depends on distance. Nearby galaxies are moving away from us slowly, while distant galaxies are moving away very quickly. This is a direct consequence of Hubble's law. Now, most galaxies in the universe are indeed moving away from us as a result of this cosmic expansion. They're receding into the distance, their light becoming increasingly redshifted, their galaxies becoming fainter and fainter as the distance increases. This applies to the vast majority of the universe, but Andromeda is different. And this is where our mystery becomes more intricate, more layered, more interesting. Andromeda is not moving away from us. Andromeda is moving toward us. Despite the fact that the universe is expanding, despite the fact that space itself is being stretched on the larger scales, Andromeda is actually approaching our own Milky Way galaxy. It's moving toward us at a velocity of approximately 110 kilometers per second, which is about 245,000 miles per hour. At that rate of approach, Andromeda is currently moving toward us, getting slightly closer each passing year. This creates a kind of cosmic paradox, a tension between two opposing forces. On one hand, we have the expansion of the universe, which tends to pull galaxies apart to increase distances between them. On the other hand, we have the gravitational attraction between the Milky Way and Andromeda, two massive galaxies that are exerting a powerful pull on each other, and currently the gravitational attraction is winning. The gravity between these two galactic siblings is strong enough to overcome the expansion of space, at least at the distances that currently separate them, and so Andromeda is approaching us, slowly spiraling toward a collision that will occur billions of years from now. Eventually, in a future so distant that the Sun will have become a red giant and consumed the inner planets of the solar system, the two galaxies will merge, combining into a single larger galaxy that some astronomers call Milkomeda or Milkdromeda. But that future merger, as fascinating as it is not the focus of our mystery tonight. Our mystery is about something more subtle and perhaps more poignant. Our mystery is about what happens to the light from Andromeda as we progress through time, as Andromeda approaches us, as the universe continues to expand. Because here's the thing about redshift and cosmic expansion. The expansion of the universe is inevitable. It's unstoppable. It operates on all scales, affecting all galaxies, all distances. And as the universe expands, it doesn't just increase the distances between galaxies, it also changes the properties of light traveling through space. Light that originates from Andromeda and begins its journey toward us will experience the effects of that expansion. The light will be stretched by the expanding space through which it travels. And that stretching of light, that transformation of light wavelengths, has profound implications for what we'll be able to see in the future. So let me ask you to imagine this with me, to really visualize this cosmic scenario. Imagine that a photon, a particle of light, is being emitted from Andromeda right now, at this moment in our exploration together. It begins its journey toward us at the speed of light. It travels through the darkness, through the expanding space that lies between our galaxy and Andromeda. As it travels, the space expands. The distance between its source and its destination increases, not because the photon is traveling slowly or being pulled backward, but because the fundamental structure of space itself is being stretched. It's like the photon is swimming against a current that's continuously pushing it backward. Except the current isn't pushing it backward. The medium through which it's swimming is itself expanding. The universe is growing larger, stretching in all directions, and that stretching affects the wavelength of the light. The light gets stretched too, in a sense. Its wavelength gets longer. It becomes redder. Now, this process is already happening right now. The light from Andromeda that reaches us today has already been affected by cosmic expansion. It has already experienced some degree of wavelength stretching as it traveled across 2.5 million light-years of expanding space. The light that reaches us is already somewhat redshifted compared to the light that was emitted from Andromeda 2.5 million years ago. But here's where it gets interesting, and where the mystery starts to deepen. If you were alive billions of years in the future, if you were to gaze up at Andromeda from the sky of a distant Earth, the light you would receive from that galaxy would be even more redshifted. The light would have experienced even more stretching as it traveled through even more expanding space. And as the redshift increases, the light shifts from visible wavelengths into infrared wavelengths, into microwave wavelengths, eventually into radio wavelengths and beyond, into parts of the electromagnetic spectrum that human eyes were never designed to perceive. At first, this might seem like merely a technical issue. After all, infrared light is still light. Radio waves are still a form of radiation. If the visible light from Andromeda becomes infrared, can't we just use infrared telescopes to continue observing it? And indeed, that's an interesting question. And we'll come back to it later in our exploration. But for now, I want you to really contemplate what this transformation means. I want you to think about the word invisible. The light is still there. It's still traveling. It still carries information about Andromeda. But it's invisible. It's invisible to human eyes. It's invisible without technological assistance. It's beyond the range of human perception. The way the ultraviolet light that gives you sunburns is invisible to your eyes. The way radio waves are invisible to you. The way the universe's background radiation, the echo of the Big Bang itself, is invisible to you unless you have specialized equipment to detect it. And eventually, even technology might not be able to help. Because as the universe continues to expand indefinitely, as redshift continues to increase without limit, the light from Andromeda will eventually be shifted so far into the infrared, so far beyond the visible spectrum, that detecting it will become increasingly difficult. There's a phenomenon in cosmology called the cosmic horizon, a limit to how far we can see into the universe. And related to that, there's the concept of the redshift horizon, a limit to how distant we can observe objects before their light is so redshifted that it becomes impossible to detect. For Andromeda specifically, while it's relatively close to us and will remain relatively close even as it approaches us, there's a limit to how long we'll be able to observe it. Eventually, as the universe expands, the light will be redshifted so severely that future observers will not be able to detect it. Not with human eyes, not with technology, not at all. The light will still be there, still traveling through space, but it will be beyond reach, beyond perception, effectively invisible to any observer in the future. This is the heart of the mystery we're exploring tonight. This is why Andromeda's light will never reach future humans, not because the light will stop traveling, not because Andromeda will be destroyed, not because there will be anything catastrophic or violent about it, but simply because the expansion of the universe is relentless, inexorable, and inevitable. Space will continue to expand. Light will continue to be stretched by that expansion, and eventually the light from Andromeda will be so redshifted, stretched so far into the infrared and beyond, that it will effectively be invisible. Future humans, no matter how advanced their technology, no matter how much they might desire to see our galactic neighbor, will not be able to perceive the light that is traveling toward them from that distant galaxy. There's something profoundly melancholic about this realization, yet also something deeply philosophical and beautiful. It means that we, here, now, in this era of cosmic time, are privileged. We are living in a moment when Andromeda's light is still visible. We can still look up and see that gentle glow with our own eyes. We can still receive, directly and immediately, the ancient photons that have travelled for 2.5 million years to reach us. Future humans will not have this privilege. They will inherit a universe in which the Andromeda galaxy, that most prominent and beloved of our galactic neighbours, will have effectively vanished from the night sky. They will live in a cosmos that looks noticeably darker, more empty, less filled with the wonder of distant starlight. And while they might still be able to detect Andromeda's existence through non-visual means, through radio telescopes or other instruments that can detect extremely redshifted radiation, they will not be able to see it. They will not be able to look up and experience that direct, visceral connection to a galaxy so distant. This realization invites us to gratitude. It invites us to appreciate what we have in this moment. It invites us to look up at the night sky with a sense of privilege, knowing that we are living in a unique era in cosmic history, an era when the universe still appears relatively bright to our eyes, when the light from distant galaxies still reaches us in visible wavelengths, when we can still maintain this direct connection to the cosmos. In billions of years, the universe will look different. The night sky will appear darker. The stars will gradually disappear, not because they've been destroyed, but because their light will have been redshifted beyond visibility. Andromeda will be the first bright neighbour to vanish in this way, a candle snuffed out not by destruction, but by the gentle, relentless expansion of space itself. And so, as we move deeper into our exploration, as we learn more about the mechanisms of cosmic expansion and the fate of light in an expanding universe, I want you to hold on to this sense of wonder, this sense of privilege, this sense of cosmic melancholy. Because these feelings, these emotional responses to the mathematics and physics of the universe, they're telling you something true. They're telling you that you are alive at a remarkable moment. They're telling you that the privilege of perceiving light from distant galaxies is not permanent, is not guaranteed, is not something to take for granted. And perhaps most importantly, they're telling you that the universe, in all its vastness and all its indifference to human concerns, still has the capacity to move us, to fill us with wonder, to make us feel connected to something larger than ourselves. The expansion of the universe is not a catastrophe. It's not an emergency. It's the fundamental way that space and time work at the grandest scales. It's the reason we exist, because the expansion that happened in the first moments after the Big Bang is what allowed matter to cool, to condense, to form atoms, molecules, stars, galaxies, and eventually conscious beings like us who can contemplate the cosmos. The expansion that we're experiencing now is just a continuation of that grand process. And yet, for all of its inevitability, for all of its natural quality, for all of its fundamental rightness, there's still something poignant about it. There's still something that touches us emotionally when we contemplate its implications. So if you're still here with me, if you're still engaging with these ideas, if you're feeling the weight of cosmic contemplation settling around you like a gentle blanket, I want to ask you to share what's resonating with you. What's capturing your interest as we explore these cosmic mysteries? Is it the vastness of the distances? Is it the relentless nature of cosmic expansion? Is it the melancholy realization that the universe we see today is different from the universe that future generations will see? Tell me in the comments. Let me know what's speaking to you, because your engagement is what makes this exploration meaningful. Your curiosity, your wonder, your willingness to contemplate the cosmos alongside me, that's what transforms these dry facts about redshift and cosmic expansion into something living, something meaningful, something beautiful. And now, as we continue to wind deeper into this exploration, as we prepare to move into the third phase of our journey together, I want you to let yourself become even more relaxed, even more comfortable. The ideas we're discussing might be vast and sometimes even disorienting, but remember that you're safe here, in this moment, listening to these words. The universe might be expanding, distances might be increasing, light might be being stretched across cosmic voids, but you are right here, right now, exactly where you need to be. You are part of this cosmos, part of this expansion, part of this grand, ongoing transformation. And that's beautiful. That's remarkable. That's worthy of contemplation and wonder and the gentle, peaceful rest that comes from understanding our place in the universe. So let us continue now into the next phase of our exploration. Let us continue learning about this cosmic dance, about the way Andromeda moves toward us, while space itself moves in the opposite direction, about the paradoxes and tensions that define our relationship with our nearest major galactic neighbor. Let us continue until we have woven together all the strands of this mystery, until we understand fully and deeply why the light that we can see tonight will not be visible to those who come after us. And in understanding that, let us understand something more profound about time, about change, about the impermanence of all things, even the vast and eternal seeming cosmos. The universe is telling us a story, has been telling us this story for billions of years, and we are privileged to be listening, privileged to be here, privileged to be able to contemplate the vastness and the beauty of it all. So let's continue that contemplation together. Let's move forward into deeper waters of cosmic mystery and wonder. Let's become explorers of the universe, not with telescopes or instruments, but with our minds, our imaginations, and our capacity to feel awe in the presence of the infinite. The universe, as we've begun to understand, is not a place of stasis. It's not a realm where distances remain constant, where the arrangement of celestial bodies stays forever the same. And yet, if you try to visualize what cosmic expansion actually means, you might find yourself struggling. How does space expand? What does it mean for the very fabric of reality to stretch? These are questions that have puzzled scientists and philosophers alike, questions that require us to think about space and distance in ways that challenge our everyday intuitions. Space, after all, is the container in which all things exist. So how can the container itself grow? How can emptiness expand? And perhaps most fundamentally, expand into what? These are the questions we're going to explore now as we move deeper into understanding the mechanism behind cosmic expansion. Because to truly grasp why Andromeda's light will eventually become invisible, we need to understand not just that the universe is expanding, but how it's expanding, what that expansion means for the very nature of space and time, and how light itself is affected by the stretching of space. We need to move beyond the abstract notion that galaxies are moving apart and into a more nuanced understanding of what's actually happening at the deepest levels of cosmic reality. Imagine, if you will, a rubber sheet. It's stretched flat, and on its surface there are dots. Let's say these dots represent galaxies. If you were to grab two opposite ends of the rubber sheet and pull them apart, what would happen? The sheet would stretch. The distance between any two dots would increase. But here's what's important. The dots themselves wouldn't be moving across the surface of the sheet. The space between them would be increasing. The dots are being carried apart by the expansion of the sheet itself. This is a useful analogy for understanding cosmic expansion, though, like all analogies, it breaks down if you push it too far. The universe isn't actually expanding into anything. Space itself is simply increasing. The quantity of space is growing. Where there was once less space, there is now more. This is an almost incomprehensibly strange concept when you really think about it. In everyday life, we think of space as a given, a backdrop against which things happen. We don't usually think of space as something that can increase or decrease. We don't think of the amount of space as being a variable that can change. And yet, on cosmic scales, this is exactly what's happening. The universe is creating more space. And as it does, all the galaxies within it are being carried apart by that creation of space. This process is called cosmic expansion, and it's one of the most profound discoveries of modern cosmology. Now, scientists have developed various theories and mathematical models to describe what's happening during this cosmic expansion. They talk about something called the scale factor, a number that describes how much the universe has expanded compared to some reference point in the past. In the very early universe, just moments after the Big Bang, the scale factor was incredibly small. The entire observable universe was compressed into a region smaller than an atom. As time progressed, as the universe aged, the scale factor increased. The universe expanded, more space was created, and this expansion continues to this day and will likely continue into the far future. The rate at which this expansion occurs is described by something called the Hubble constant, named after Edwin Hubble, the astronomer we mentioned earlier. This constant describes how fast galaxies are receding from us as a function of their distance. The farther away a galaxy is, the faster it's moving away from us, and the Hubble constant tells us the precise relationship between distance and recession velocity. For every megaparsec of distance, and a megaparsec is about 3.26 million light-years, galaxies recede from us at a velocity of about 70 kilometers per second. This might not sound like much when stated in these abstract terms, but when you apply it across cosmic distances, it means that galaxies billions of light-years away are receding from us at velocities that approach or even exceed the speed of light. Now, this might seem to contradict Einstein's principle that nothing can travel faster than light. And that's a good instinct. Nothing can travel through space faster than light. But cosmic expansion doesn't involve things moving through space at faster than light velocities. Instead, it involves the space itself expanding. The galaxies aren't moving through space at superluminal speeds. The space between them is increasing, which has the effect of causing the galaxies to recede from each other at rates that can exceed the speed of light. This subtle but crucial distinction allows for the possibility of cosmic expansion rates that exceed the speed of light without violating Einstein's relativity. What all of this means, in practical terms, is that the universe is fundamentally dynamic. It's changing at every moment. The distances between galaxies are increasing, the amount of space is growing, and this growth continues regardless of what's happening within space, regardless of the activities of stars and galaxies and conscious beings contemplating the cosmos. The expansion is woven into the very fabric of space and time. It's described by Einstein's equations of general relativity, the same equations that describe gravity, the curvature of space-time, and the fundamental structure of reality. And here's where it becomes relevant to our story about Andromeda. Because as space expands, as the universe creates more room for itself, light traveling through that expanding space experiences effects. Light carries energy. Light has wavelengths and frequencies, and when space expands, those wavelengths get stretched. The wavelength of a photon, a particle of light, is directly related to the distance between successive peaks of the light wave. When space expands, that distance increases, the wavelength increases, and when wavelength increases, the frequency decreases, which means the light becomes redder, less energetic, shifted toward the infrared and beyond. This is the mechanism behind the redshift we discussed earlier. It's not that the source of the light is moving away from us, although in the case of distant galaxies, both effects are happening simultaneously. It's that the space through which the light is traveling is expanding, stretching the light waves as they journey across cosmic distances. This is called cosmological redshift, and it's distinct from the Doppler redshift that occurs when a source is moving away from an observer. The distinction is subtle but important for really understanding what's happening. Now, as we contemplate this cosmic expansion, as we think about what it means for light traveling through expanding space, we can begin to see the shape of our mystery taking form. Andromeda is currently moving toward us, closing the distance at a rate of about 110 kilometers per second. This means that the gravitational attraction between our galaxy and Andromeda is currently stronger than the effect of cosmic expansion pushing them apart. But is this situation permanent? Will gravity always win this battle against expansion? Or might there come a time when expansion overwhelms gravity, when the distance between us and Andromeda begins to increase despite the gravitational pull between them? The answer, as it turns out, depends on the nature of the universe's expansion. Specifically, it depends on whether the expansion is accelerating, decelerating, or remaining constant over time. In the early days of cosmology, after Hubble's discovery, scientists assumed that cosmic expansion was slowing down. They reasoned that the gravity of all the matter in the universe would create a kind of cosmic drag, gradually slowing the expansion that began with the Big Bang. Over vast timescales, they thought, gravity might eventually reverse the expansion entirely, pulling all the galaxies back together in what was called a big crunch. This would be the opposite of the Big Bang, a moment of infinite density and temperature when all the matter and energy of the universe came back together. But in the late 1990s, astronomers made a remarkable discovery that challenged this assumption. By observing distant supernovae, exploding stars that serve as standard candles for measuring cosmic distances, astronomers found that the expansion of the universe wasn't slowing down. It was speeding up. The universe was accelerating in its expansion. Galaxies were being pulled apart faster and faster as time progressed. This discovery was so unexpected, so counterintuitive, that it initially met with skepticism from the scientific community. but subsequent observations confirm the finding. The universe is indeed accelerating in its expansion. This acceleration is attributed to something called dark energy, a mysterious form of energy that permeates all of space and has the effect of pushing space outward, causing it to expand faster and faster. Dark energy comprises about 68% of the total energy and matter content of the universe, making it the dominant component of reality. And yet we understand almost nothing about it. We don't know what it is, we don't know where it comes from, we don't know if it's truly constant or if it might change over time. Dark energy is one of the deepest mysteries in modern physics, a profound unknown that underlies the very structure and fate of the cosmos. But we don't need to fully understand dark energy to grasp its implications for Andromeda's future. We just need to recognize that the expansion of the universe is accelerating. Galaxies that are very far away are being pulled apart faster and faster, and while Andromeda is currently approaching us due to gravity, at some point in the distant future, this situation will change. As the acceleration of cosmic expansion continues, as space stretches faster and faster, the gravitational attraction between Andromeda and the Milky Way will become increasingly insufficient to overcome the expansion. Eventually, the expansion will dominate. The distance between us and Andromeda will begin to increase, slowly at first, then more rapidly. Andromeda will transition from approaching to receding, from moving toward us to moving away. This transition point is important to our understanding of what will happen to Andromeda's light, because once Andromeda begins to recede from us, once the distance between the galaxies begins to increase due to expansion, the light from Andromeda will experience a different kind of redshift. The light will be stretched not just by the expansion of space through which it travels, but also by the recession of the source itself. The redshift will increase more rapidly. The light will become redder and redder, shifting from visible wavelengths into infrared and beyond at an accelerating rate. Now, estimates for when this transition will occur vary depending on the specific parameters of cosmic expansion, but most calculations suggest that Andromeda will reach its closest approach to the Milky Way in roughly 4.5 billion years. At that point, the two galaxies will begin to merge. They will spiral into each other, gradually combining into a single larger galaxy. During this merger process, which will take another few billion years to complete, the situation will be complex. Gravity and expansion will be battling for dominance in an increasingly intricate dance. Eventually, however, assuming that cosmic expansion continues to accelerate as current observations suggest, the expansion will win, the merger will complete, Andromeda and the Milky Way will become one, and that unified galaxy will begin to recede from other galaxies around it as space continues to expand. But here's what we need to focus on for our purposes tonight. As Andromeda begins to recede, as the expansion of space starts to dominate over gravity, the light from Andromeda will be increasingly redshifted. The visible light will shift into infrared. The infrared will shift further into the microwave region of the spectrum. And eventually the light will be so redshifted that no technology, no matter how advanced, will be able to detect it. The light will still be traveling, it will still carry information about Andromeda, but it will be beyond the reach of observation. It will be invisible not because it's been destroyed or because Andromeda has vanished, but because the universe's expansion will have transformed the light into something that's effectively undetectable. To understand this more deeply, let's think about what happens to light traveling through expanding space in more concrete terms. Imagine a photon emitted from Andromeda at a particular moment in cosmic time. This photon has a certain wavelength, a certain frequency, a certain amount of energy. As it begins its journey toward the Milky Way, it immediately encounters the expanding space. Space is stretching everywhere, in all directions, at all scales. The stretching of space causes the wavelength of the photon to increase. The photon becomes less energetic. Its wavelength becomes longer, shifting it toward the red end of the visible spectrum and eventually beyond into infrared. Now, the amount of redshift that a photon experiences depends on how much space expands during its journey. If the photon travels through space that expands by a factor of 2, the wavelength of the photon will also double. If space expands by a factor of 3, the wavelength triples. And as the universe continues to age, as cosmic expansion continues, the amount that space expands over any given distance continues to increase. Light that travels the same distance today will experience more redshift than light that traveled the same distance in the past. This is because the universe is expanding faster and faster. What this means for future observations of Andromeda is profound. The light from Andromeda that reaches us today has been redshifted somewhat, but not dramatically. Most of it remains in the visible spectrum, which is why we can see it with our eyes. But light from Andromeda that begins its journey toward us 1 million years from now will experience more redshift by the time it reaches us, assuming Andromeda is still close enough that light can reach us in a reasonable time frame. Light that begins its journey 1 billion years from now will be even more redshifted. And light that begins its journey when Andromeda has begun to recede due to cosmic expansion will be extremely redshifted, shifted so far into the infrared and beyond that it will be impossible to detect with any technology we can imagine. Eventually, as billions of years pass, as cosmic expansion continues to accelerate, the light from Andromeda will be so redshifted that it will effectively disappear. We won't see a dramatic moment when Andromeda vanishes. Instead, it will be a gradual fading. Night after night, over billions of years, the light from Andromeda will become slightly redder, slightly dimmer, slightly harder to detect. Eventually, it will fade below the threshold of detectability. It will enter a realm of invisibility not because the light has stopped traveling, but because the universe's expansion will have stretched it so far from its original wavelength that human eyes and human instruments will no longer be able to perceive it. There's something quite poignant about this scenario when you really contemplate it. It means that the Andromeda Galaxy, our nearest large galactic neighbour, our cosmic companion that has guided astronomers and stargazers for centuries, will eventually vanish from the observable universe. Not because it's being destroyed, not because it's moving infinitely far away in any absolute sense, but simply because the expansion of space will have stretched its light to such an extent that it becomes invisible. Observers in the distant future will look up at the night sky and will not see Andromeda. They will see other galaxies, other stars, other cosmic phenomena. But that one bright, familiar spiral galaxy that we can see with our own eyes today will be gone from their view. And yet, there's also something beautiful about this. There's something that speaks to the fundamental nature of the universe itself. The expansion that will eventually render Andromeda invisible is the same expansion that created the universe in the first place. It's the same mechanism that allowed matter to spread out, cool down, and eventually form the galaxies and stars that make up the cosmos as we know it. The expansion that will take Andromeda from our sight is the same expansion that brought galaxies into existence in the first place. It's the grand, ongoing transformation of the universe, the unfolding of space and time in the vastness of existence. So as we continue our exploration, as we prepare to move even deeper into the specific timeline of Andromeda's fading and the scientific observations that support our understanding of this phenomenon, I want you to sit with this contemplation. I want you to really think about what it means that we are living in a moment in cosmic history when Andromeda is visible to us. We are living in a brief window of time, a window that will eventually close. Future generations will not have what we have. They will not be able to look up and see, with their own eyes, that gentle spiral galaxy. The privilege of that vision is ours. It belongs to this era, and in a way, that makes it all the more precious, all the more worthy of wonder and gratitude. The universe is breathing, space is expanding, distances are increasing, light is being stretched, and we are here, conscious observers, capable of understanding these processes, capable of recognizing our place within them, capable of feeling awe at the grandeur of it all. That's remarkable. That's something worth contemplating as you drift deeper into relaxation, deeper into the peaceful space that this exploration creates. Now, before we move into the specifics of Andromeda's approach and eventual recession, before we map out the timeline of its fading, I want to pause and acknowledge something. The ideas we're discussing might seem abstract, might seem removed from the everyday concerns and experiences that occupy our lives. We are focused on timescales of billions of years, on processes that operate on cosmic scales, on forces and phenomena that are so far beyond our normal experience that they can seem almost like fiction, like mythology, like something that belongs to the realm of imagination rather than concrete reality. And yet, these are not abstract ideas. These are descriptions of the actual behavior of the actual universe. These are the real mechanisms that govern the cosmos, and understanding them changes something fundamental in how we experience the world. When you look up at the night sky, after understanding these concepts, when you see Andromeda, if you're in a location dark enough and clear enough to perceive it, you're not just seeing a pretty light in the sky. You're seeing something that's traveling through space, that's expanding, something that's being affected by dark energy and cosmic acceleration, something that's participating in the grand transformation of the universe. You're seeing something that won't be visible to future humans. You're seeing something precious and temporary and beautiful precisely because of its temporality. This realization can be humbling. It can make us feel small, insignificant, lost in a vast cosmos that doesn't care about our concerns. But it can also be liberating. It can make us recognize that we are part of something immense, something wonderful, something that deserves our attention and our wonder. It can make us grateful for the opportunity to be alive in this moment, to be conscious, to be aware of our place in the universe, to be able to contemplate these cosmic mysteries. And so, as we move forward, as we begin to map out the specific timeline of Andromeda's future, I want you to remember this sense of perspective. I want you to remember that what we're discussing is not theoretical in some distant abstract way. It's the real behavior of the universe in which you live, the universe through which you move, the universe that you are part of. The expansion that will eventually make Andromeda invisible is happening right now. The redshift that will eventually shift Andromeda's light beyond detectability is already occurring. We are living in the midst of these processes, even though we don't usually notice them, even though they operate on timescales so vast that they're invisible to our human perception. Let me pose a question to you now, something to contemplate as we continue our journey. If you're still here with me, if you're still engaging with these cosmic ideas, if you're finding value in this exploration of the universe's expansion and Andromeda's future, I'd like to know what has struck you most powerfully so far. Is it the realization that the light from Andromeda is ancient, that it's been traveling for 2.5 million years? Is it the concept of cosmic expansion, the idea that space itself is stretching? Is it the melancholy realization that future humans won't be able to see Andromeda? Is it the philosophical implications of all of this? What it means for our understanding of time, change, and impermanence? Or is it something else entirely? Please leave a comment and let me know. Your responses help me understand what resonates with you, what speaks to your sense of wonder, what draws your curiosity toward the cosmos. Because contemplating the cosmos is not a solitary activity, even when you're alone, even when you're listening to this in the quiet of the night. It's something that connects us across time and space, across the barriers that normally separate us. When you contemplate the same mysteries that I'm contemplating, when you think about the same cosmic phenomena that astronomers and physicists are studying, you're joining a conversation that has been ongoing for thousands of years. You're adding your voice to a chorus of human consciousness, seeking to understand the nature of reality, and that's beautiful, that's meaningful, that matters. So let's continue now. Let's move deeper into understanding the specific way that Andromeda will approach us, the way it will eventually begin to recede, and the timeline over which this transformation will occur. Let's map out in detail what the future holds for our relationship with our nearest galactic neighbor. Because to truly understand why Andromeda's light will eventually become invisible, we need to understand not just the mechanisms involved, but the specific trajectory that this cosmic dance will follow. We need to understand the billions of years of motion and change that lie ahead for Andromeda and the Milky Way. We need to see in our mind's eye the slow unfolding of events that will eventually transform the night sky. And as we do this, as we contemplate these vast timescales and cosmic motions, let yourself become even more relaxed, even more at peace. The distances we're discussing are vast, the timescales are incomprehensible, but you don't need to comprehend them intellectually in order to feel their weight, to sense their significance, to understand intuitively what they mean. Let your mind drift into these cosmic spaces. Let yourself float in the darkness between stars, in the expanding void between galaxies. Let yourself become one with the expanding universe, one with the light traveling through space, one with the slow, inevitable transformation of the cosmos. Because in a real sense, that's what you are. You're made of stardust, formed from the remnants of ancient stellar explosions. You're part of the universe becoming conscious of itself, contemplating its own nature. And that connection, that unity with the cosmos, is something worth feeling as you drift deeper and deeper into contemplation and peace. The night sky above is one of humanity's oldest sources of wonder. Long before we had telescopes, before we had the means to understand the physics behind what we see, humans looked up at the stars and felt something profound. They felt awe. They felt connection. They felt a sense of being part of something larger than themselves. That impulse, that drive to look up and wonder, is still alive in us. It's still part of what makes us human, and it's no less real and no less powerful now that we understand the physical mechanisms behind what we're seeing. If anything, understanding makes the wonder deeper. It makes the connection more meaningful. It makes the cosmos more beautiful, because we're able to see not just what it looks like, but how it works, how it transforms, how it evolves over cosmic timescales. So now, as we prepare to move deeper into our exploration, as we begin to map out the specific timeline of Andromeda's approach and eventual recession, keep this sense of wonder with you. Keep this sense of connection. Keep this feeling of being part of something vast and beautiful and profound, because that's what we're really exploring tonight. We're not just exploring the physics of cosmic expansion and light redshift. We're exploring what it means to be a conscious being in a universe of incomprehensible size and age. We're exploring what it means to have this brief window of awareness, this moment in cosmic history, when we can perceive the beauty of the cosmos. We're exploring what it means to know that this window will eventually close, that future humans won't have what we have, that we are privileged in a way that is both beautiful and melancholy. And in that exploration, in that contemplation, we find something that transcends the merely intellectual. We find something that touches us emotionally, that moves us profoundly, that makes us feel connected to the universe in a way that goes beyond words or concepts or scientific equations. We find, in short, a reason to be grateful for the opportunity to exist, to perceive, to contemplate, to wonder. And perhaps, as you continue to listen to this exploration, as you continue to drift deeper into the cosmos and deeper into sleep, that gratitude is what you'll take with you. That sense of privilege, that sense of wonder, that sense of being part of something beautiful and vast and ultimately mysterious. The universe is speaking to you through light that has traveled across incomprehensible distances. The universe is showing you phenomena that only a few generations of humans have had the tools and the knowledge to understand. The universe is inviting you to contemplate mysteries that may never be fully solved, questions that may never be completely answered, wonders that may never be fully grasped. And that invitation, that opportunity, is a gift. Treasure it. Wonder about it. Let it move you. Let it change how you see the world. Because in doing so, you're participating in one of the most beautiful aspects of human experience, the drive to understand, to explore, to contemplate, to grow beyond what we are toward a greater appreciation of what is. Now, as we move forward, let me guide you deeper into understanding what the future holds for Andromeda. Let me paint for you a picture of the cosmic drama that will unfold over billions of years. Let me show you, step by step, how a galaxy that is currently approaching us will eventually begin to recede, how the light from that galaxy will gradually shift from visible to invisible, how the night sky of the future will be different from the night sky of today, and in contemplating that future, let us contemplate our own place in it, our own significance, our own role as observers and contemplators of the cosmos in this particular moment in time. The Milky Way and Andromeda are locked in a gravitational embrace. This embrace has been ongoing for billions of years. It will continue for billions of years more. But the nature of that embrace is changing. Right now, the two galaxies are approaching each other. Their gravity is pulling them together despite the expansion of the universe pushing them apart. But this situation is not permanent. As we've discussed, the expansion of the universe is accelerating. The rate at which space stretches is increasing, and eventually gravity will no longer be strong enough to overcome this acceleration. The two galaxies will begin to recede from each other. But before that happens, before that transition occurs, the two galaxies will collide. They will merge. The dance between them will reach its climax. This merger is estimated to begin in about 4.5 billion years from now. To put that in perspective, the Sun is currently about 4.6 billion years old. The Sun has perhaps 5 billion years left before it exhausts its hydrogen fuel and becomes a red giant. So the merger of the Milky Way and Andromeda will occur roughly around the time that the Sun is dying, if not after it has already died. This is a timescale so vast that it's almost incomprehensible in human terms. But on cosmic scales, it's relatively soon. It's a cosmic event that's already been set in motion, that's already inevitable, that's already written into the mathematics of the universe's expansion and the gravity between these two massive galaxies. The merger itself will be a cosmic event of tremendous significance, but it won't be dramatic in the way that you might imagine. It won't be like two cars crashing. There won't be explosions or sudden cataclysms. Instead, it will be a slow, graceful process that will unfold over billions of years. The two galaxies will spiral toward each other, driven by their mutual gravity. As they approach, tidal forces, the differential gravitational force across the extent of each galaxy, will begin to distort them. They will stretch and warp and take on strange shapes. Stars will be pulled out of their orbits. Gas clouds will be heated and compressed. New stars will form in regions of intense compression. Eventually, after several billion years of spiraling, the two galaxies will merge into a single larger galaxy. The exact nature of this merger, the details of what the resulting galaxy will look like, depends on the specific dynamics of the collision. But based on simulations and observations of similar galaxy mergers in the universe, we can make some educated guesses. The resulting galaxy will likely be elliptical in shape, lacking the distinctive spiral arms that both the Milky Way and Andromeda currently possess. It will be larger than either of its parent galaxies, containing all of their stars, all of their planets, all of their cosmic matter mixed together into a new configuration. For life on Earth, assuming life still exists at that point, the merger will have profound consequences. The gravitational dynamics of the merger will likely disturb the orbit of the Earth around the Sun, possibly moving it to a different location in the solar system. The influx of new stars into the region where the Milky Way currently resides will brighten the night sky significantly. Instead of the relatively sparse distribution of bright stars that we see today, the night sky of the far future Earth will potentially be ablaze with starlight. The night might become almost as bright as day. This will be a dramatic change to the experience of looking up at the sky, a transformation that will alter the visual appearance of the cosmos as seen from Earth. But here's what's important for our purposes tonight. Even during this merger, even as the Milky Way and Andromeda are combining into a single galaxy, Andromeda's light will still be reaching us. The light from Andromeda will still be visible, or at least mostly visible, for the entirety of the approach and the early stages of the merger. Because Andromeda is still relatively close to us on cosmic scales, the light only takes 2.5 million years to reach us. Even billions of years from now, even after the two galaxies have begun to merge, Andromeda's light will still make the journey across the shrinking distance between us in times that are relatively quick on cosmic scales. However, and this is the crucial point, as the merger progresses, as billions of years pass, as the expansion of the universe continues its inexorable acceleration, the situation will begin to change. Eventually, the two galaxies will complete their merger and form a single unified galaxy. At that point, the gravitational forces that have been driving them together will no longer apply. Gravity will no longer be pulling them together because they will be together. They will be one, and at that point, the expansion of the universe will be the only force acting on the merged galaxy. The merged galaxy will begin to recede from its neighbors. The distance between the unified Milky Way Andromeda system and other galaxies around it will begin to increase due to cosmic expansion. And as the distance increases, as the recession velocity increases due to the acceleration of expansion, the light from what was once Andromeda will begin to shift more and more toward the red end of the spectrum. The redshift will increase. The light will become dimmer and dimmer in terms of its observable properties. And eventually, after billions of years of recession, after the expansion has continued to accelerate, the light will be so redshifted that it will be invisible. It will have shifted so far into the infrared and beyond that no human eye, no human instrument will be able to detect it. Andromeda's light will have faded from the universe. But here's what makes this particularly melancholy and beautiful. By the time Andromeda's light has faded completely, by the time the merged galaxy has receded so far that its light is invisible, the universe will have changed dramatically. The night sky, as observers at that future time will experience it, will be vastly different from what we see today. The stars visible to the naked eye will have gradually disappeared, one by one, as cosmic expansion has redshifted their light beyond the visible spectrum. The expansion will have continued, accelerating, driving galaxies and stars farther and farther apart. The universe will be older, colder, darker. Observers in that far future, if they still exist, will look up at a night sky that is almost empty of visible light. They will be living in a cosmos that has undergone a profound transformation from the one we inhabit. This future, hundreds of billions of years away, incomprehensibly distant, is sometimes referred to as the far future or the deep future. It's a cosmos so different from our current one that it's almost difficult to imagine. Yet it's a future that's written into the mathematics of the present, a future that's already determined by the laws of physics as we understand them, a future that will come to pass if the universe continues to behave as it currently does. Now, you might ask, what is the evidence for all of this? What observations have led scientists to believe that Andromeda is approaching us, that the universe is expanding, that cosmic expansion is accelerating, that dark energy is pushing space apart? These are good questions. They get at the heart of the scientific method. How do we know what we know? How can we be confident in these conclusions when we're talking about processes that unfold over billions of years, processes that we cannot directly observe in their entirety? The answer is that science has developed sophisticated tools and techniques for observing the universe and measuring its properties. We have telescopes that can observe distant galaxies and measure the speed at which they're moving. We have instruments that can analyze the light from Andromeda and determine its motion relative to us. We have observations of supernova explosions in distant galaxies that have allowed us to map the expansion history of the universe. We have measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, that tell us about the state of the universe in its earliest moments. All of these observations fit together into a coherent picture, a picture that tells us how the universe works, how it has evolved, and how it will continue to evolve in the future. The evidence for Andromeda's approach, specifically, comes from measurements of its motion. Andromeda is approaching us at a velocity of about 110 kilometers per second, which was determined through spectroscopic observations of its light. The light from Andromeda is slightly blue-shifted, meaning it has been compressed by Andromeda's motion toward us, shifted toward higher frequencies and shorter wavelengths. This blue shift tells us directly that Andromeda is moving toward us. The amount of blue shift tells us the velocity of that approach. These are direct, measurable observations, not speculations or guesses. The approach of Andromeda to the Milky Way is something that we can observe and measure. It's not a theoretical prediction, it's an observed fact. The evidence for cosmic expansion comes from Edwin Hubble's observations in the 1920s, and it has been confirmed and refined by countless observations since then. Hubble observed that distant galaxies are redshifted, which we now understand to mean that they're moving away from us due to cosmic expansion. The farther the galaxies are, the greater the redshift, which is consistent with the idea that space is expanding and that the expansion rate increases with distance. These observations have been refined by later astronomers, and the relationship between distance and recession velocity, the Hubble constant, has been measured with increasing precision over the decades. The evidence for accelerating expansion came from observations of distant supernovae in the late 1990s. Supernovae are extremely bright stellar explosions that can be seen from billions of light years away. They serve as what astronomers call standard candles, objects of known brightness that allow us to measure the distances to distant objects. By observing the brightness of supernovae at various distances, and by measuring the redshifts of those supernovae, astronomers were able to map out how the expansion rate of the universe has changed over cosmic time. They found, surprisingly, that the expansion rate was not slowing down as had been expected. Instead, it was speeding up. The universe was accelerating in its expansion. This finding was so unexpected that it initially met with skepticism, but subsequent observations have confirmed it. The acceleration is real. The universe is indeed expanding faster and faster. This acceleration is attributed to dark energy, a mysterious form of energy that pervades all of space. Dark energy comprises about 68% of the total energy density of the universe, making it the dominant component of reality. And yet we understand almost nothing about what it is. We have some ideas. It might be the energy of the quantum vacuum, a kind of zero-point energy that exists in empty space. Or it might be something else entirely, something that we haven't even conceived of yet. But whatever it is, it's having the effect of pushing space apart, causing the expansion to accelerate. So when we say that Andromeda's light will eventually be redshifted beyond detectability, When we say that the expansion of the universe will eventually render Andromeda invisible, we're not speaking from abstract theory. We're speaking from observations, from measurements, from data collected by astronomers and scientists who have dedicated their lives to understanding the cosmos. We're speaking from a body of knowledge that has been built up over decades, that has been tested and refined and confirmed again and again. We're speaking from as close to certainty as science can get when discussing phenomena that operate on timescales much longer than human existence. And yet, and this is important, there is always uncertainty in science. There is always the possibility that our understanding will be refined, that new observations will lead to modifications of our theories, that something unexpected might be discovered that changes how we understand the universe. Science is not absolute. It's not the final word. It's a process of inquiry, a method for understanding nature, a conversation between observation and theory that continues perpetually. As we learn more about the universe, as our instruments become more sensitive and our observations more precise, our understanding may change. But based on the evidence we have right now, based on the observations and measurements that have been made, the picture that emerges is clear. Andromeda is approaching us. The universe is expanding, and that expansion is accelerating. And therefore, Andromeda's light will eventually be redshifted beyond detectability. This is where the evidence leads us. This is what the data tells us. And this is the future that lies ahead for our cosmic neighbor and the light that reaches us from it. So as we move deeper into contemplation of Andromeda's specific future, as we begin to map out in more detail the billions of years of change that lie ahead, let us do so with both intellectual understanding and with a kind of humble acknowledgement of the limitations of that understanding. We're doing our best to comprehend a universe far older and far larger than ourselves. We're attempting to understand processes that operate on timescales that dwarf human existence. We're reaching forward with our minds, with our observations, with our science, trying to grasp something of what lies ahead for the cosmos. And that effort, that striving to understand, that reaching toward knowledge, that's beautiful. That's what makes us human. That's what connects us across generations. That's what drives us to explore, to discover, to contemplate mysteries that may never be fully solved. And so, wrapped in this understanding, feeling the weight and wonder of it, let yourself continue to relax even more deeply. Let your mind drift across billions of years. Let yourself contemplate the vast timescales involved, not with anxiety or fear, but with a sense of peaceful wonder. The universe is large, time is vast, we are small, and yet we are here. We are conscious, we are capable of understanding, we are connected to all of this. And that connection, that awareness is a precious thing. Hold on to it as you drift deeper and deeper into contemplation and into sleep. Hold on to the sense that you are part of something immense, something beautiful, something that has been unfolding for billions of years and will continue to unfold for billions of years to come. The dance between the Milky Way and Andromeda is a cosmic ballet that has been in progress for billions of years and will continue for billions of years more. It's a dance choreographed by gravity and dark energy, performed on a stage of expanding space, witnessed only by conscious beings like us who have learned to see and understand what's happening. And we are privileged to be observing this dance at a moment when Andromeda is still visible, when its light still reaches us, when we can still perceive it with our own eyes and contemplate its place in the cosmos. This privilege is not permanent. This window of visibility will eventually close. But for now, in this moment in cosmic time, we have it. And that is something truly remarkable. End.